Just look up at the midday sky. It's this brilliant, deep blue, right? Then fast forward to the evening, and suddenly the horizon transforms into this burning, blood-red sunset. It almost feels like the sky is changing its clothes. But here's the thing. The sun emits white light. Just white. In the middle of the day, the sun's actual color is white, meaning it's a blend of every single color of visible light. When that light hits the ground, it usually just looks like plain white light, which is really just a combination of all the colors of the rainbow. So if the light coming from our star is basically white, why on earth does it change colors? By the end of this episode, you'll start to see a sunset differently. You'll actually observe the invisible filter working in real time. To understand why the colors shift, we have to look at the invisible ocean of gas surrounding us. I mean, our atmosphere is basically a precise chemical cocktail. The main components are 78% nitrogen and 21% oxygen. These two gases completely dominate the mix, with a few percent of other things like carbon dioxide floating around. Now, this list of ingredients sounds simple, but these tiny molecules of nitrogen and oxygen are actually the architects of the sky's color. They're everywhere, billions upon billions of them, acting as a microscopic sieve that sunlight must navigate before it even reaches your eyes. It's honestly wild to consider that something we can't even see is the sole reason we perceive the sky as blue. Back in 1859, a physicist named John Tyndall did something interesting. He shined a beam of white light through a container filled with smoke. He noticed that the light scattering off the sides appeared blue, while the light coming out the other end seemed reddish. This simple experiment really laid the groundwork for understanding atmospheric optics. Years later, in 1871, Lord Rayleigh developed the mathematical proof for this. He calculated exactly how particles smaller than the wavelength of light interact with that energy. Rayleigh basically connected the dots between Tyndall's observed blue light and the physical properties of the molecules in our air. His math transformed a simple curiosity into a proven physical law. Now, we have to get into the physics of it all. Light energy travels in waves, specifically electromagnetic radiation consisting of vibrating electric and magnetic fields. If you look at a light bulb or the sun, the light may look white, but that white is just a blend. It's the spectrum of visible light, which consists of all the colors we can see, blending continuously into one another. If you use a prism, you can pull those colors apart. You'll see the 7 colors of the spectrum: red, orange, yellow, green, blue, indigo, and violet. But here is the key. Each color has a physical shape. Red light waves have peaks that stay far apart. It's the longest wavelength in the visible spectrum, stretching from 620 to 750 nanometers. On the other hand, blue light waves are shorter, choppier. It's a total contrast in physical form: long, lazy red waves versus short, energetic blue ones. Think about the invisible collision. When sunlight hits Earth's atmosphere, white light encounters a chaotic sea of tiny air molecules. This is where the scattering process begins. These gas molecules, specifically oxygen and nitrogen, are incredibly small, about 2,000 times smaller than the wavelength of light. This is where the physics of Rayleigh scattering takes over. Some particles in the atmosphere match the size of blue light wavelengths, or roughly 1/10 the size of the light's wavelength. When light hits a particle of this specific size, it doesn't just pass through. It reflects or scatters in every direction. Since the gases in our air primarily scatter those shorter, choppier waves of blue light, those waves create the blue color we see. That's the reason the sky looks blue. Blue light is selectively scattered into the air by atmospheric particles. During the day, the stars are invisible because this scattered blue light makes the atmosphere glow, masking the view of the stars behind it. Now, if the short, choppy waves are the ones getting scattered, you'd think the sky would look purple, right? Because violet light has an even shorter wavelength than blue. This is where the physics of light meets the biology of your own eyes. Inside your retina, you have two types of photoreceptors, rods and cones. The rods handle the intensity and shades of light, while the cones handle the color. Specifically, your retina uses RGB cones to split incoming light into combinations of red, green, and blue. Because our eyes are actually more sensitive to blue than violet, the scattered light we perceive as a brilliant blue is actually a mix, which our biological hardware filters into the color we recognize. As the sun drops lower, the path length of light through the air becomes longer. It has to fight its way through a thicker slice of our atmosphere. The light travels through layers that might have a higher concentration of dust particles, making the journey far more chaotic. The blue light just doesn't survive this longer path. A longer path through the air results in even more scattering of the blue. By the time the light finally hits your eyes, the blue light has been scattered out and removed from the beam. This explains why sunsets appear red or amber. So much blue light has been scattered away, leaving only the red, orange, and yellow side of the spectrum to survive the journey. The scattering of blue light at sunset allows the more orange and yellow light to pass straight through the atmosphere to our eyes. At twilight, the sky becomes a deeper blue because more blue light is removed from the sun's light. It's really a matter of subtraction. The atmosphere acts as a filter, scrubbing the blue away until only the crimson remains at the horizon. Now, there's a reason why some sunsets look like a muted pink and others look like a terrifying blood red. It all comes down to the junk in our air. While we talked about gas molecules, there are also aerosols, particles in the air. NASA's Earth-observing satellites monitor these aerosols to track changes in our atmosphere. When these aerosols, like dust, pollution, or smoke, are present in high concentrations, they scatter massive amounts of blue light. This creates a glowing red sky with brilliant reds that can feel otherworldly. Paradoxically, a sunset that isn't deep red might actually be the result of too many particles in the air, depending on the size and type of these particles. It's a strange irony that the very things we call pollution can actually beautify the horizon in dramatic ways. It's easy to forget that the air we breathe is actually an incredibly thin layer. The official definition of space begins at 62 miles, about 100 kilometers above the ground. That height is roughly the distance from New York to Boston, yet we call that the thickness of our atmosphere. To put that in perspective, if you held a globe where the distance from New York to Boston was 180 miles, the altitude of the International Space Station would be about 3/8 of an inch. We live inside a shield that functions like the skin of an apple or the shellac on a globe. It's a fragile, narrow strip of gas that creates the entire light show we just described. If you think Earth's colors are strange, just imagine standing on the surface of Mars. The Martian atmosphere is thin and filled with iron-rich dust particles. These particles are larger than the molecules in our air. They cause what's called me-scattering, a process that's different from Rayleigh scattering. While Rayleigh scattering favors short blue waves, me-scattering affects light differently based on the size of the particles. On Mars, the dust particles scatter red light away, meaning the light that survives the journey is dominated by blue hues. Consequently, the midday sky on Mars is a butterscotch yellow, and the sunset is a haunting, cool blue. It's a perfect inversion of our own experience, caused by the exact same laws of physics interacting with a different atmospheric composition. The atmosphere is more than just a filter, it's a complex lens. Take the green flash. This is an atmospheric optical phenomenon that happens briefly at the very top of the sun's disk as it disappears below the horizon. It happens because of the refraction of light through the atmosphere, where the air bends the different colors of the spectrum at slightly different angles. For a fleeting moment, as the red and yellow are blocked by the horizon, the green wavelength remains visible. It's a transient, elusive event that serves as a reminder that our sky is constantly bending, scattering, and filtering light in ways we're only beginning to quantify. We've traveled from the midday brilliance of a deep blue sky to the crimson hues of a blood-red sunset, and it all comes down to a chemical cocktail of 78% nitrogen and 21% oxygen. The sky isn't actually blue. It's a visual trick played by Rayleigh scattering, where short, choppy blue waves are bounced around by tiny molecules. When the sun dips, the light has to travel through a much thicker slice of our atmosphere, scrubbing the blue away until only the long, lazy red waves survive the journey. We're protected by a layer of air only 62 miles thick, a fragile skin of gas like the shellac on a globe that transforms white light into a vivid light show. The color of our horizon is really just a signature of our planet's composition. I wonder if this delicate balance of atmospheric gas determines the limits of what we can actually perceive.